Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
Welcome back, everyone. This is Week 7, Part 2, and today we are diving deep into the Transformer Blueprint. This isn't just another model in a long line of them. Nope, this is the fundamental architecture that's powering pretty much every major AI breakthrough you hear about, from the large language models you chat with, all the way to AI that generates unbelievable images. So here's our plan for today. First, we're going to look at the problem that older models just couldn't crack. Then, we'll lay out the full Transformer blueprint, and we're going to take it apart piece by piece, the encoder and the decoder. And finally, we'll see how this one elegant design became the foundation for a whole family tree of AI. All right, so to really get why the Transformer was such a game changer, we have to go back and understand the big problem it was built to solve. It's a problem that really held back all the models that came before it. Okay, so over on the left, you've got the old way of doing things with models like recurrent neural networks, or RNNs. Think of them as reading a sentence one word at a time, trying to cram the meaning of everything they've seen so far into a single tiny memory. Well, this created a massive information bottleneck. By the time the model got to the end of a long paragraph, it probably forgotten what the first sentence was about. But on the right, you see the Transformer's genius solution. Just look at everything at once. Every word can directly talk to every other word, completely shattering that bottleneck. And this is really the heart of the matter. With an RNN, for the last word to know something about the first word, that information has to travel down a long, winding path, getting weaker at every step. But with the Transformer, the path between any two words is always just one direct hop. This direct connection isn't just more powerful, it unlocks the ability to process everything in parallel, which is absolutely critical for training the giant models we have today. Okay, so with that problem in mind, let's pull back and look at the actual schematic of this machine we're about to explore. And here it is, the full blueprint. Now, I know it looks a little intimidating, but let's just break it down. It really has two big halves. Over here on the left, you've got the encoder stack. Its only job is to read and understand the input. Then on the right, you have the decoder stack, which takes that understanding and uses it to generate something new. We're going to walk through every single one of these boxes. This quote just nails the whole philosophy. Instead of forcing the model to cram everything into a compressed memory, you just let it look back at the source material. Every single time it needs to make a decision, it can revisit the entire input. It's kind of like giving the model a permanent open book test. The answers are always right there for it to reference. But wait, this brings up a huge question, right? If you're looking at all the words at the same time, how does the model know their order? I mean, the dog bit the man is very different from the man bit the dog. The solution is this really clever trick called positional encoding. Before anything else happens, we literally inject a little signal into each word that tells the model its exact position in the sentence. It's like stamping every word with a coordinate. All right, let's zoom in on that left side of our blueprint, the encoder. Its entire purpose in life is to read the input sequence and build a really deep contextual understanding of it. Now, the encoder isn't just one block. It's actually a whole stack of identical layers, and each of these layers does two main things. First, you have multi-head attention. This is where all the words get to look at each other and share information. And then there's a feed-forward network that processes each word's new updated information individually, kind of getting it ready for the next layer up the stack. This diagram, this right here, is the engine at the very heart of the Transformer. It's called scaled dot product attention. Here's a simple way to think about it. For every single word, the model generates a query. Think of it as a question, like, who is the one doing the action here? It then compares that query to a key from every other word in the sentence. And wherever it finds a good match, it pulls in that word's value. It's a super sophisticated way for the model to decide which other words matter most for understanding the current word. But here's where it gets really clever. The model doesn't just ask one question at a time. It has multiple attention heads, all working in parallel. And each head can learn to focus on a totally different kind of relationship. So you might have one head that's an expert in grammar, another one that tracks who did what to whom, and a third that's just focused on what the pronouns refer to. It's like having a whole team of specialists analyzing the sentence all at once. Okay, so after the attention step lets all the words talk to each other and get updated, each word's representation is then passed through its own little private feed-forward network. So if attention is about communication between words, this step is all about computation within each word. It's just a chance for each word to think for a moment and process everything it just learned before passing it up to the next layer.
All right, so the encoder has now done its job. It's created this incredibly rich, context-aware representation of the input. Now we can shift our focus over to the right side of the blueprint, the decoder. Its job is to take all that understanding and generate a brand new sequence, one word at a time.
At first glance, a decoder layer looks pretty familiar, right? It's got multi-head attention, it's got a feed-forward network, but there are two really important differences. First, its own attention mechanism is masked. We'll see what that means in a second. And second, it has this extra component wedged in the middle called encoder-decoder attention. And that is the bridge to the encoder.
So think about it. When a model is generating a sentence, it has to predict the next word based only on the words it's already written. It can't just peek into the future, right? That would be cheating. This is where the look-ahead mask comes in. It literally blocks the attention mechanism from seeing any of the future words in the sequence it's creating. This forces it to generate text one step at a time, just like we do.
And this is the magic link. This middle block is where cross-attention happens. In this step, the decoder forms a query based on the text it has generated so far. But, and this is the key part, it sends that query over to the encoder, which provides the keys and values from the original input sentence. The decoder is essentially asking the encoder, hey, based on what I've written so far, what part of the original input should I be paying attention to right now to pick the perfect next word? Now, this powerful and super flexible design turned out to be so much more than just a better way to do machine translation. It became a universal blueprint for computation, giving rise to this entire family of different models, each one adapted for different kinds of tasks.
And get this architecture isn't just for text. The vision transformer, or VIT, showed that you can apply the exact same logic to images. The trick is brilliant. You just slice an image up into a grid of patches, and then you treat that sequence of patches exactly like a sentence of words. You feed that sequence into a totally standard transformer encoder, and it just learns to read the image.
And this slide really shows the deep philosophical difference. On the left, older image models like CNNs were built with this hard-coded assumption, this inductive bias, that they should only look at little local groups of pixels. But on the right, the vision transformer has no such bias. It's completely free to learn relationships between any two patches in the image, no matter how far apart they are. It learns the entire visual world from scratch, directly from the data. So this flexibility means you can just use the building blocks you need for the job. If your task is all about deeply understanding some text, like figuring out its sentiment, you can just use an encoder-only model like BERT. If your task is purely about creating new text from a prompt, you can use a decoder-only model like GPT. And if you need to transform one sequence into another, like in translation, well, that's when you use the whole shebang, the full encoder-decoder stack. So when you boil it all down, it comes back to just a few core elegant ideas. You've got the attention mechanism, so elements can talk to each other, the feed-forward network, so each element can think for itself, and some clever engineering like residual connections to let us build these models really deep. This fundamental shift away from slow, one-at-a-time processing to fast, all-at-once attention is what truly unlocked the modern era of AI.
I mean, this architectural jump from serial to parallel processing is exactly what enabled the unbelievable scaling we've seen in AI. And it really makes you wonder, if this single blueprint can learn to understand language and vision just by treating them as sequences, what's next? What other kind of data, from DNA and protein folding to financial markets and music, can be understood through the lens of this universal architecture?